Hello, I'm David Goldsmith, and welcome to Project Moonhot and Mearth Infinium. Today we're going to be discussing the illusion of moon and asteroid mining, and then everything you wanted to know about mining. Now, before we begin, there's a few points we need to discuss. The first is humanity needs resources, and they're all here on Earth. And in order for you to understand how we extract them and we use them, you need to understand how we mine. So you'll be learning about the full scope, the constraints, and the realities. Once we're done, we'll travel beyond Earth, and we'll even cover some of the types of technology that we can use to move forward. Now, this deck is dense, so there's a copy of a PDF below if you'd like to download it and review it later. So let's start with a simple construct of why does this deck exist? The world is fighting over materials, and decision makers who are making those decisions often don't understand or acknowledge the challenges of mining. And then others are proposing solutions that just won't work. So in order for you to be able to make better decisions for yourself, this deck will give you that clarity. So we have to start right at the very beginning. What is mining? Mining is the extraction of materials from Earth. Simple. We extract materials from Earth. They could be metals used for infrastructure, electronics, and transportation. They could be minerals used for agriculture and energy. They could be used for fuels that power our communities, our homes, our industries. We use mining everywhere. So if you look around at your desk or the place you're sitting today, I can guarantee you that everything around you has been mined. You looked out a window today, that's silica. The nails that hold everything together or the steel that we have, that's mined. If you drove a car, that's mined. The dishes, the doorknobs, the bolts, the wires, all of those are mined. And the machines that make them are mined. The equipment that we use to transport them in is mined. The tools that we have is mined. The energy to power them is all mined. We use mining everywhere. But let's expand that so we have a better understanding of the definition of mining. We're not going to review anything below the line, but I want to target them just for a moment. When we go into a forest and we cut down trees for lumber, we are mining, or for toilet paper. When we plant organic excavators or seeds, what we're asking the seed to do is pull the minerals and nutrients out, and then we're going to harvest them and eat them. If we were involved in fishing, well, we're mining the ocean so that we can eat. Oceans also give us things such as sand, gravel. They give us nickel, iron, and cobalt. We mine the oceans. So without mining, there's no materials. With no materials, there's no civilization, at least the way we know it. And since the beginning of time, we've been always challenged with this, we're running out, we're running out. Go back 100 years ago, they were saying it. Go back 500 years ago, they were saying it. We're constantly in this fear-mongering state that we're running out of materials. So the best way to start about understanding materials is to go to the very beginning. Theia crashed into the Earth 4.5 billion years ago. The particles scattered all over, and then they formed into the moon. That formation over time, that debris that was sent out, gave us the moon that keeps us a rotational axis, gives us the gravity that we have, makes our tides move. The women's biological cycles, animals, we all are influenced by the moon. It's a part of how we live. Now, that's not to say it's a resource for us, but we also found a redistribution of Earth's elements. The collision helped redistribute all of the gold, platinum, and rare metals towards the Earth's, they sank towards the Earth core, but they gave us on the crust enough that we can survive for billions of years. Now, with that said, we have three different types of rock that are formed. There's igneous, metamorphic, and sedimentary. A miner is looking for igneous rock and metamorphic rock. That's where the concentrations are the highest. So the resources that we have when you think about mining can be looked at this way. Everywhere you look, there's material. You walk outside, there's material that can be used for mining. The challenge is concentration. That's a big one. If you were on a beach right now, you could be reaching down and take out a grain of sand and move it to the side and take another grain of whatever's there. And eventually, maybe on the billionth try you did it, you'd find maybe some gold in it. The challenge is when you're working in environments where capital is involved, time, resources, you can't work at that scale. So what a miner does is look for a concentration or an ore body. That ore body is a large enough concentration that it can economically be extracted. Now, my background, a little bit, of it for you is that I ran a rock quarry down near New York City when I was younger, and we dropped 22,000 tons of stone a day. Now that is, to get your mind around it, 250 of those American long trucks and semi trucks. It also was 12 to 24 scows going down the Hudson River. This is rock. This is used for construction. It is used for roads. It is used for foundations. This is rock. And 22,000 tons was about 92% of all stone going to New York City. But the entire world drops 100 billion tons of rock per year. I can't even fathom that, and I was involved in the mining of rock. It's a lot. So there are 3 different types of rocks that you might want to look at. One of them is 4 different types: construction rock, ore, surface, and deep. They require a different type of work necessary to be able to make that possible so that we can use them. Construction rock, which I was dropping, was immediately taken and used. We had some processing afterwards, but very minimal. We had to break it into different sizes. Ore rock, which includes metal, rare earths, and for electronics they're used for, is high. It takes a lot of energy and a lot of processing. Surface ore mining, lithium, rare earths, moderate to high, and deep rock mining that's below the surface is very high and very costly. And if you were to look at the world today, just using a pie chart here, you see that there's coal, there's iron ore, there's gold, there's copper. The rare earths are that very top sliver, and it's less than 1% of what's out there. You're not going to see on this list germanium or bismuth, but bismuth is used for stealth aircraft. It's also used in nuclear shielding. A typical military aircraft can use 800 pounds of the types of materials that are necessary that are very difficult to be able to find. And so how do we start this process? Well, throughout history, miners have been looking for resources, and they've been mapped into this map here, which gives you a sense of where we're guessing the highest concentrations are. The most dense, and you look for, is the orange, then the pink, and then the green. And if you look at Canada, it's called the Canadian Shield. These are called shields. You'll see that Canada is full of rare earth materials and the very challenging materials we're looking for. So is Greenland. There's not much in Central America. You'll see in South America, it's pretty concentrated. Africa has a tremendous amount. The challenge is there's no infrastructure, there's no energy, there's no processing, which while being available, it needs a full infrastructure to develop. You'll see very limited in Europe, Asia, and you'll see some in India and then Australia. So the world is not full of the materials in equal distribution, and we have to extract from those places. Now, the challenge becomes this. When you're doing a mine, it is a gamble. 1 in 10 will survive and bring the big money in. But a mine takes 15 to 30 years to form. 15 to 30. I want you to remember those numbers. So when you read that someone found something and they've got this huge deposit, that deposit won't turn into anything for 15 years from today. And that's a challenge because you're given promises that won't be fulfilled. And even when they do extract, oftentimes they don't find what they had expected. And so this is a gamble. And these are mines throughout Australia. Every one is a projection of a gamble of what's possible underneath. And a whole ecosystem has to be built in order to make this happen. So why is this important? Why is mining so important? Well, today it's come up because of the new technologies we've developed and the needs for battery and electronics. Those are forcing new questions for energy and storage and advanced tech for our supply chains. And one organization did some math and they say we need 293 mines by the year 2030. I just shared with you that a typical mine takes 15 to 30 years. And we need, in the numbers below, for copper, lithium, nickel, cobalt, rare earths. And we also, what we need in terms of numbers, but we also need processing facilities. That's a whole nother game we're going to go into. So let's drop down a little bit further so you can understand how mining works. First, what we do is we put on front of a helicopter far enough away so it's not picking up the helicopter signal itself. We use a magnetometer. what the magnetometer does is it travels across the surface, and it's looking to identify anomalies that it can find, magnetic anomalies. And so its applications are for mineral exploration, industrial data, agricultural surveys, environmental remediation, military operations, and geological research. It's not just for mining, but it's a tool that enables us to find at least where the materials might be. But they do fail huge in a variety of different areas. They can't detect lithium, copper, or rare earths or gold. So what happens is it's flying over and giving a sense of what's available. And with that, and after review, individuals decide that what they're going to do is now walk. And they go in and they start to look at ground surveys. They pull out samples, start to look for ore bodies. They start to look for the density and the hardness. Remember the rocks that they were looking for. They're looking for hydrology, water in the rock. They're trying to look at chemical composition. And they're taking a guess to say, in that spot where we think something is, there is something worth pursuing. And then the real work begins. The first thing you're going to want to do, or act two, after you've done that survey, is you're going to want to dig core samples. Now, these can go 1,000 to 4,000 feet deep. And what we're doing is we're pulling out a core sample to say, what's inside of that? Is it worth going down? And then what we do is we take technology to evaluate it. We're looking for a tiny sense of what's inside of it, because that sample is going to say that at 500 feet, at 1,000 feet, at 2,000 or 4,000 feet, there's something there that can be pulled. The challenge is often, even though that information comes up, it might not find the ore body that we're looking for. So once we do one, we do many. We could do 300, 500, 700 core samples. And what we're looking for to find is we're looking to find that there's a high enough concentration of an ore body that's worthwhile to mine. And this is extremely expensive. If in fact we find something, what we do is with all of those samples, as we start to sample them in a core shack, is we start to map them out and we say, what's available down below? And with all those holes, we're trying to get a fair sense of, is this worthwhile? A French mining company recently invested $800 million into developing a mine. And when they got there, they found nothing that's worthwhile. What happened was when they were drilling, they don't go completely straight. They were all curving in a way that they couldn't find material. So $800 million, and there was nothing below the surface. What they're looking to do, what a miner's looking to do, is create a type of map, something where they could see where all the materials might be so that they can take that material and decide how it's going to be extracted. And there's all different types of extraction that's necessary. In this mapping, we now know what's necessary and the cost that it's going to take. Remember, we haven't mined a thing yet, but there's a challenge with mining. Everything that we do in mining requires some types of formulaics. There are hundreds of formulas that at 1G, we could figure out how to drop rock, what it takes to be able to work in that type of environment. And there's one main formulaic that we work off of, a formula. It's called the bond work index. Every mining calculation comes from it, and it requires Earth's gravity. So this tool here enables everything that happens in mining. So from that, once the individuals believe that there's something below, there's all different types of dropping of rock, but I'm just going to give you one type that uses gravity. What you're doing is you're blasting below the materials, and the materials fall down on the bottom left-hand corner. But this is often for low-grade material. So we must extract a lot of material in order to have some type of value on it. And there are all different types of sophisticated mining approaches. This is not just a simple, you walk in, find some material. You have to understand how the earth will react and what types of material you're working on and what types of equipment you need. Now, what we've discussed so far could be $50 to $100 million. A typical mine development cycle is 15 to 20 years just to get to the point of saying we're going to dig and extract and pull out. So let me give you some clarity just for the sake of it very early on so that you could see or think about what it would take if we would go to the moon. Now, in 1972, we had the Apollo series, and the deepest we've ever mined on the moon is 292 centimeters, about 3 meters, which is about 9 feet. The Earth is huge. The moon is 3,474 kilometers. We have gone down 3 meters, 9 feet. So the total sum of all the knowledge about the moon for humanity comes from these core samples. That's it. And by the way, the drill broke. So that is mining 101 on the moon. So let's take a step back and give a perspective. Let's take a look at the Earth here. The Earth is 8,000 miles wide. So a typical mine is about 4,000 feet deep, and it requires a tremendous amount of energy to be able to get down there. What I'm going to do is take the image on the right, and I'm going to take you through where we sit as humans today. But what I'd like you to do is imagine you're sitting where you are today, in the chair you are today, or standing if you may be. But I want you to imagine you're that tiny little point that you're looking at. That's you. So when we're thinking about mining, this would be how the constructs or the environment would look like. Most of our mining goes less than 4,000 feet deep. It gets hot. The pressure is extreme. So that is most mining worldwide is less than 4,000. The deepest mine we've ever gone is 2.48 miles down, and that's about 4 kilometers. That's the deepest mine we work in. If you go to number 3, the deepest drill depth we've ever gone to is 40,230 feet. It became extremely hot, and the drill bits wouldn't work because it requires friction, and the Earth becomes more like a silly putty. It moves. The temperature went from all the way down to 212 to 356 Fahrenheit, or 100 C to 180 C. It's very hot down there. If you go to number 4, the Marianas Trench is just shy of that, at a little shy of 40,000 or 7 miles down. And the Mount Everest is 5.5 miles tall, or 8.9. That's at 26,400 feet. If we were to take that, the Manhattan Island in the United States, Manhattan Island is about the same length, if you added those two up, of the distance that we've gone down for the entire world. So you're not seeing depth. We haven't gone anywhere. And if you were to think of the whole world, the Earth is 8,000 miles wide. We are not touching any of the resources that are underneath. That means that the possibilities of what's below us are extreme. So let's now talk mining, now that you've got a sense of where we are and what's available to you. We're going to go over shafts, equipment, depth, and tunneling. So when a mine, or the decision to make a mine, happens, especially down below the surface, what we do is we dig holes. Look at how huge this is. They cost about $50,000 a foot. And we're going to be going upwards of 4,000 feet. So the initial cost of a shaft could be about $250 million to $1 billion. Those numbers in the mining industry are not considered extreme. And then as we move down, we go further. Look at these massive structures. Look at how big they are. And they go further down. And they're constantly going down and down, down. So you can imagine how long it takes to go this deep. It's dark, it's hot, and it's far. Now, once we get down to the depths that we like, we have to start going sideways. And we have to start creating a tunneling system, somewhat like a subway system. This becomes the infrastructure in which we work in. So if you look at the equipment on the bottom left-hand corner, that has to be disassembled and then reassembled below. It's expensive. And if you looked at the shaft's sizes above, you can imagine how small these pieces had to be. Then they're reassembled and used. Those are used to create the shafts. These shafts are your base camp, the dispatch. It's a nerve center underground. It's a workplace for thousands or hundreds of people, and it's going down extremely deep. This is once you find material, it's moved to the shaft and then brought up, or through a series of where you can drive up on ramping. Now, some individuals believe that this is something that happens very quickly. And one individual believes that they want to create a tunnel from New York City to London. And this piece of equipment on your right, the fastest one we have on Earth, does 14 feet a day. A day. That would take us, if you did the math, from New York City to London, 3,586 years. Yes, we can improve it. There are chances, but we do have some challenges. First of all, it's going to be extremely far down. There are lava tubes and air drafts, and the heat and pressure that we'll encounter below will be tremendously difficult on the individuals working there. But we're not done yet. We now have to build tunnels to get to the materials that we're looking for, and that requires even more equipment that's brought down. Once we get to that point, we now start mining. All of that before we mine the thing. So think about the infrastructure that has been developed in all of the tunneling systems, whether it be Hong Kong, whether it be the UK, the United States. You think about all the subway systems. They take a lot of time and energy. And now we start mucking a tunnel face by putting in rods about 14 feet and blasting the rock out. And a small to medium shaft, 220 million to 50 million, very small. But if we're talking the types of material that we need to scale for the Earth, we're looking at 300 million to a billion. Some of the numbers change here based upon the way in which I was creating the slides, because the numbers are not fixed, but it can go up to about $1 billion. Now that you've seen the infrastructure, let's take a step a little bit further. Now we mine. So mining isn't one size fits all. It's not. There's different type of rock. There's soft rock and hard rock. But we also have to put up protective mechanisms for those who are mining so that no one gets hurt. This is an example of that type of safety that's put in place. Hard rock requires one type of equipment, soft rock another. You can imagine the types of materials that are down there. So if we're doing soft rock and we can now excavate it out, that allows us, such as a salt mine, to be able to pull out the material in high volume. And it's just pushing it forward, pulling it down, and then it's extracted and brought to the surface. But if we were to go to coal, now we've got a different type of mining extraction. But look at the size of this equipment and look what's taken down. I live south of Lake Ontario, of the Great Lakes. There is a salt mine. The estimated amount of salt that's available is 800 years worth. There's a tremendous amount, and you need high volume extraction equipment to be able to make that happen. But hard rock requires a whole different philosophy, a whole different approach, because you're blasting the rock out to get the materials. So there are extreme challenges. Rocks to break them clean, it's very difficult. And it doesn't just show up the way individuals think. So for example, this is a map of a narrow vein mining situation. This is gold. And if you were to look at them, those little lines that you see, that's where the gold vein is. So that wall is about 15 meters or 45 feet wide. And you drop the entire set of rock so you can bring out the gold extraction. But let's take a look at it, because we're looking at grams here. If you look there, that's 0.07 grams per ton. So you drop a ton of rock and you're going to get 0.07. Then there are higher concentrations. You can see that little pink. That little pink is to say, well, it's high there. But overall, you're going to take down all of that wall to be able to get it. Now, narrow vein mining equipment, new technology that we're working on, will enable that to extract differently. But all that rock has to be processed. And you might think gold looks like this. It does not. This is very, very rare to see high-grade nuggets this size. What you really do see is you see this. See, gold is found in parts per million and parts per billion. It's inside of rock that is dropped. And then that rock has to be taken and brought and processed. This brings up the cost, but we still haven't gotten it out of the ground. So there's a tunnel system that allow the ramps to bring up through all different types of tech to get it to the surface, which is extremely expensive. You think about walking uphill. Well, you need energy. Energy is a cost. And then there's other type of vertical machines that allow this to skip, will enable you to pull the materials up from the bottom of wherever you found it. Now we have to get to breaking rock. Now we've just brought it to the surface. All that is just to get it to the surface. Approximately up to 3% of all energy on Earth is used just to break rock for all those things that you need that are around your home, that are around your life. So what we do is we bring it to the surface. And if you look at the humans in the bottom left-hand corner, you'll see the scale of these. The rock is dropped into a primary. The primary then crushes it. Small pieces, medium pieces, large pieces come out of it. And you can look at the top right, you could see another type of crusher. And the machine on the bottom is now going to be sorting it. And what's taken out are the materials that are small enough that could be used in other processing. So and then going to, if it's from the bottom of a deep mine, that could also go for processing to find out if there's other materials in there. But then some of those rocks don't break up as small as we'd like, and we send them to a crusher. Again, energy. In the mining operation I was in, these were huge pieces of equipment that would take rocks that are 6 feet wide, and they would break them 2 meters, and they would crush them into smaller, and then we go to a secondary, and then we'd sort. So you've now gotten the rock up there, and we've broken it down, and that's not even the crazy part. Now what we do is we take that, if we're going to be processing it for the types of rare earths that we're looking for, what we do is we put them into an autogenous mill. These pieces of equipment can be 30 to 80 feet high diameter and 100 feet long. And you put them in, and you put rocks inside, or cannonballs or rods. And what you're doing is you're breaking the rock into finer and finer material that can then later be processed. This requires gravity because as it's spinning, the rock is falling on itself. Then it's taken to a flotation cell. And this is where you'll see that water and chemicals are used and gravity to be able to separate out what's necessary. This plant is easily $100 million to several $100 million. This is the type of processing that is needed on Earth just to be able to separate, or the beginning of separation. Again, it gets crazy. So we've got the feedstock. You saw the primary, the secondary, the autogenous mill, and now we're liberating in the baths that you've seen. And out of that, there's going to be more. You're going to get rejected material, the thing that's worth money, the money stuff. And then there's a tailings pile, the waste that's tossed off. That is the balance of it. So there's not much. You're going to get 5% or less of what comes out. Remember, then it gets complicated. See, that previous slide, that 5%, then it goes to furnaces, so it can be dried out. Then it's put into another set of furnaces, and then it's crushed again, and then it's flattened again, and it's smelted, and then it's sorted again. This whole process, and I'll show you on the bottom left-hand corner, all the way, all this material that you've just been looking at has to go through this process and then separate it out. What chemicals were used that were not used in the process. And then finally, you bring it to a refinery. Now you're at a refinery. Now those smelters are huge. They require a tremendous amount of energy. So an average smelter can use about 350 megawatts per year to operate. Look at the scale, size, and scope of that. All of that's done to just get it to the point where it can be used in the, for example, lithium plant. So this is an example of one of those refinery type systems. Top right, you have copper. And on the bottom behind me, as I move myself away, a typical lithium, a new lithium plant was just approved in the United States. And they were given a loan, and it's $2.26 billion just for the lithium plant. Look at the size of what we're talking about in order to make that happen. So it's not a simple process that individuals are making it sound like, well, we'll just make it happen. What is in our world today, China has played, while the world was playing checkers, China was playing chess. They went out and they built the processing plants. These don't just pop up overnight. They require a tremendous amount of work. And so kudos to them. They played the game well. Now the game needs to be changed. But that's just one process. I can show you all different processes. Each type of material we're getting or we're trying to process has a different formulaic to it. Each one, and that's another challenge to be able to make that happen. Once we're done with the material, those types of things that aren't being used, they're put into a thickener that allows it so it won't seep down into the ground. And then in some parts of the world, China is one of them, they don't spend as much time on making sure that the chemicals are absorbed or they're taken care of. This isn't a blame of blaming a nation. That's not why they're up here. They're up here because these are easy to find. It's decisions that individuals are making. So please don't take this as a slam on someone. All sorts of countries have all sorts of challenges, and that's not a blame for Project Moonhot to sit in. We probably can go around the world and say that there's challenges everywhere. In this case, those materials seep outside and they go down and they're not processed, which decreases their cost of processing. Now that you've seen all of that, I want you to just look at a simple Tesla battery, the Y battery. You need to mine about 12 tons of rock for lithium, 12 tons for copper ore, 5 tons of cobalt, 3 tons of nickel ore. So you need to move about 250 tons to get what goes into a battery. And today, by the time of making this, it takes about 7 years for an electric car to reach net zero CO2 because it takes 264 gallons of diesel for a Caterpillar 994A to be able to do the work that it needs to in a 12-hour period. But even many of the types of mining that we are engaged in, for example, cobalt is found in the DRC. And in Africa, they're using child labor as well as human labor to be able to extract it. Again, not a statement, it's just clarity. So if you want to have a sense of who you are and where you engage in this, just to create your iPhone, it takes about 50 tons of material for one iPhone. You are part of the mining ecosystem. Now, this is a picture in 2023 of mining cobalt. The Democratic Republic of Congo, this is a picture. There's about 255,000 men, women, and children that are involved in the extraction. Today, the cost of using humans is cheaper than using equipment. If that changed, this picture would change. If there was a piece of equipment that can do what this group of individuals do, or somebody else can extract it cheaper, this picture wouldn't survive. But today, mining is still based in the 1980s and 90s. It's fairly archaic. But let's take a jump to the ocean mining. Ocean mining also has challenges. What we do is we extract from the oceans, and you have big vessels that go onto the ocean floor, on the surface, and then they extract in different types of technology. So we have some technology that the material is sucked up from the bottom, it's processed on, and the extra is tossed off. But we can go fairly deep doing that, and bigger ocean vessels are used to be able to make that happen. Behind me, what you're seeing is that machine from the previous slide. It goes along the surface and it picks up, say, nuggets that it finds on the surface. We've been able to find that once that happens, it takes an extremely long time. I mean, it could take centuries for that area to be able to be re-inhabited. So it's not a simple, we just mine the ocean and it works. Besides that, all of what I've showed you before is going to be so difficult if you're going to do that at the bottom of the ocean. So when someone says that they have found $30 billion, $26 billion beneath the sea that can power economy for decades, I want you to think about what you've just seen before. Finding the materials is one thing. On land, it's 15 to 30 years to become operational. Underwater? Geez, what are we talking about? Don't even know. What's under the sea may be worth billions, but getting it out might cost us more. We have to look at the future differently. So let's take a jump to the moon. This is where we got moon and asteroid mining, and I hope that you've seen there's a lot that goes into making this happen on Earth. So we're shifting our focus. Hope you're ready for it. So we're going to go back to that first slide. Moon and Earth hit, they collided, and we ended up with the moon and the Earth the way it is today. So think of it this way. And the Earth is a rock in space, and so too the moon. Now, for geophysical definitions, wanted to make sure we didn't get anybody upset here, that we could say the moon is a planetary satellite planet and the Earth is a planet. But if we use those terms on Earth, I mean, if you were to have an alien come, they wouldn't call it planet. They might call it a rock. We've defined it that way. So just think of them as rocks because we're talking about mining. We're not talking about that. And I want to jog your memory. Remember, the drill broke. We've only gone 3 meters below the surface. That's it for the entire moon. So the total sum knowledge of the moon comes from these samples, and the drill broke. But let's take a look at the composition. Might help you. If we were to look at that chart on the right, you'll see Earth's oxygen level 45.2, the moon is 44.7. Silicon is 22.1, and the moon is 22.5. Now, those little arrows were stuck in later so that to say we're almost even, we're close. Now, for those who like to be picky, we didn't put the close on the 6 to 8.2, and that's iron, but it doesn't make a difference, and neither do any of the others. They tell a story of what's available on our planet. And 30 to 40% of all the nickel that has been used comes from an asteroid that hit the Earth near Sudbury, Canada. 30 to 40% of all the nickel on Earth comes from one asteroid that hit the planet. So if someone says they're an expert in moon or mining, ask them, how many drill holes have they performed 1,000 feet deep or more on the moon? And it's going to get some people upset, but writing papers does not make a miner. And I have been told constantly since I've been involved in Beyond Earth, I know nothing about mining. I ran a quarry. I didn't drop the heavier materials, but I knew that the process it takes is far more exceptional than what's being led to believe. Now, one of the people on our team who's helped us get to this point is Greg Baden. I would say he's probably the #1 mining expert underwater, on land, high altitude, low Earth orbit, and the moon. He knows more about mining than anybody I've met worldwide. He was asked to go to NASA, and he was asked if he could he could take over their mining operations. They had 400 people in that audience. And what he asked them was very simple. He said, in the room of 400, what's the first thing a miner does? You know the answer already. Now, they can do the magnetometer. They could do that. But what they do is they drill core samples. They make holes. So he asked them, how many 1,000-foot holes have been drilled to the moon? And it was silence. Greg has been responsible for 160,000 core samples. You cannot mine if you don't know what you're drilling into. It's not complicated. Now, what we've looked at also, Greg and I, as we work together, is that he calls himself a recovering asteroid miner. What is a recovering asteroid miner? A recovering asteroid miner is we mine asteroids that have hit Earth. So we already know the compositions of different types of asteroids. We don't know, and when we think about it, we don't know what's up there. We don't know the inertial systems that work. We don't have a GPS system if we were to go to the moon. We need 80 to 100 satellites to be able to do it properly. We'd have to do all the processing on the moon, because if you're going to drop all that rock and get 0.07% grams per ton, it'd have to be processed there. We have no formulas to work on the moon. We don't have metallurgy that will withstand the temperatures. And I'll be going over all of this for you to see how crazy this is. So let's look at the Sudbury Basin that we're looking at. I talked about the nickel earlier. This one plot of land is where you're going to find most of that material. And it was formed by an asteroid 1.849 billion years ago. And if we were to go to the moon, we'd have to find something like this. And the only way to find it is to drill those holes. So let's talk about mining on the moon, and not to make a statement, but to add clarity. So the moon and to mine on the moon, we need the same processes we do on Earth. As far as we know today, no one has come up with anything different. We have to find it, mine it, extract it, crush it, separate it, and refine it. I think that's pretty clear at this point, correct? We have all of these formulas, but all of the formulas are based on gravity. and there is zero gravity on the moon, or relatively zero. So that means this equation that we looked at earlier is requiring Earth's gravity, now has to add something to it. The reality is that the bond work index, if it's relying on it, the calculations fail. And based upon our math, to process material in space, this formula would require an impossible amount of energy because the conditions have changed. We have hundreds of formulas to do the work here over thousands of years, and we don't have anything to do the mining on the moon. So the exclamation point here is to say, here's a statement you might want to think about. But we also have individuals talking about water on the moon and how thick regolith is, and it's 4 to 5 meters and 10 to 15 meters. How do they know? How do they know? We don't have the tools on Earth. We don't have the tools on Earth to do this. How are they figuring this out? Show us the proof. How do you know it's 15 meters deep? So these are questionable when you start to read these documents. And part of that first drilling is that we have to drill down to get those core samples. And when we're drilling, we use gravity and atmosphere to do some of our work. So a drill bit like this will not work on the moon. We have atmosphere to suck the stone out. We use gravity to be able to get that penetration. These won't work on the moon. We don't have a single bit that would work on the moon today. We cannot take Earth to the moon. So this is a challenge. We also have great pictures. There's individuals who send pictures all the time. This is called the Robotic. It's a massive machine in this picture. Can you just imagine how many rockets it would take to get that machine up? And humans would have to assemble it up there. Besides that, these machines are very temperamental, so you'd have to have individuals working on it. It's massive, and it would cost tens of billions of dollars to ship it there. But look around in the picture. There's no vehicles to move materials around. They don't operate well on Earth. And these temperatures, the metals, the hoses, the fluids would all disintegrate. Look at that picture. That is 71.7 degrees Celsius. And we're talking minus 120s and plus, the math is on the next one. It's escaped me for the moment. So let's take a look at this rotopella. It's called a bucket wheel excavator. The reason we know they're temperamental is because we use them on Earth. They're temperamental. They require a lot of work. They break down. The teeth break down. There's all sorts of technology pieces that wear. So there's no air. It's 130C, no moving vehicles. There's no fluids or hoses. I mean, all of this won't work. So imagine they don't have any of that. That little conveyor belt system has to go to someplace. All of this has to be built. So while it sounds great, looks nice, someone likes a great picture, I'm going to put this down as we have to rethink this. The amount of trucks that it would take for the volume that comes off of that would be astronomical. Remember, we also have to process it. And all the sophistication, this gravity and vacuums and systems that we're using on Earth, the block cave mining that we talked about earlier, not going to happen. We'd have to rethink all of that. So that's another challenge. But we also hear a lot about Shackleton's crater. I can't tell you how many times someone says Shackleton's crater is the answer. Well, Shackleton's crater is 1.2 kilometers deep. It has a 70% incline. On Earth, to get equipment 1.2 kilometers deep at a 70% incline would be extremely difficult. And at the base, it's going to be about 88 Kelvin or minus 298 C. Our batteries would freeze, our fluids would fail. Humans can't operate. We'd use helicopters to get the equipment down if we had something on Earth. There is no way that we're going to pull anything out of Shackleton's crater in the near future. One day, maybe, not saying it's not possible, but we have to question that. But we also have this hope and hype of helium-3. It's sought after. It's important. It's going to be the energy of the future. Now, you can read through some of this later, but I want to focus in on just one area, and that is this bottom right-hand side. So in order to be able to create with helium-3, you need some math behind it. 1 kilogram of helium-3 would give about 19,000 megawatts or 19 gigawatts of power. Now, to power New York City, you need about 11 gigawatts of energy, which is about 580 kilograms of helium-3. Why is helium-3 so valuable? What you want to do is you want to take helium-3 with deuterium, and that's going to create an energy system that has no radiation. And it will be the future of energy if it can be developed. So let's do some math for you. Helium-3 extraction. We've done the math. It would take to get about 1 kilogram. 1 kilogram. Remember, we had almost 600 we needed. It would take to drop about 50,000 ton of rock to get 1 kilogram, which is about 2.2 pounds. For some of you, it's about the weight of a pineapple or a bottle of water. So you need 50,000 ton, but it could go up to 1 million based upon concentrations. You've already learned that it's not an equal distribution. So 50,000 ton of rock, to give you a feeling of what would you need, you'd need about 2,000 to 2,200 US semi-trailer loads, depending on what we're talking about in terms of the material we're dropping. You need 22 million bricks. You need 1 kilogram is nothing. So it's sci-fi speculation. This organization put $18 million into this machine. This machine is supposed to extract helium-3 and then bring it back to Earth. You'd have to ship that piece of equipment to the moon. And then what are you going to do with it? Extraction? We don't have the technology to be able to do that today. But let's make it even a little bit more challenging. There's no working helium-3 reactor. There's no demonstration reactor. There's no scalable extraction system. There's no commercial pipeline. There's no helium-3 energy economy. So while helium-3 does exist in low concentrations, it's low based upon mining standards, and that makes it even more challenging. So great, we can talk about helium-3 and powering the world. What I'm going to do is I'm going to say, let's think about that for a moment and get some more information. So kind of the way you might want to look at it is the moon is not Earth. And based upon what you've seen so far, is this mining or is it boys with toys? We're trying to take what we do on Earth and extrapolate it to the moon. And everything has to be redesigned. So Caterpillar's autonomous vehicles may be used by NASA to mine on the moon, but there's got to be an entire system that's developed. It's far more complicated than we're being led on to believe. So now let's talk about processing on the moon, and you know this is going to get worse. So we need an endogenous mill. The endogenous mill breaks it up into smaller pieces. Could we develop something new? Yes, we are talking about that right now. But if it's 1/6 gravity, we would need to have the rock spin up. It would go up to the top and fall down. Well, then in order to be 1/6 gravity, it would, instead of being 30 to 80 feet high, it would be 180 to 300 feet high. So imagine we'd have to build a structure 300 feet high to be able to do the endogenous mill. So that's a challenge. We have the flotation cells. You've seen them. This whole process. There's no gravity for separation, no vacuum for processing. There's water scarcity on the moon, temperature extremes. We have massive infrastructure needs. We have maintenance issues. We've got dust and contamination. We've got launch costs. All of this would have to be factored in to the first part. A challenge. But we'd have the same processing after that. All of this would have to be built. And you've seen the size of those factories. What we're doing, each type of ore has its own process. So we'd have to figure out what we're going to do for each one. Another challenge. And often we talk about water ice. So this is also not a simple solution. There are calculations out there, they vary. But let's say there is some water out there. It's locked with other materials that have to be separated. We could find somewhere in the neighborhood of 10 in 1,000 parts per million, but we're talking about very little. So in order for us to make this happen, for every, let's say, ton of material, we'd get a drop of water. That's a crazy number. Let's start thinking about our future in a different way. And another challenge is if we could find the water ice and get it out. One of the things that happens when you drill on the moon is the minute you break the surface, everything evaporates. And you've got a phase diagram of water on the bottom, so you'll see how the temperature and the conditions would mean that everything would go into space. It would disappear. We can't, the way it's being sold, get water ice off the moon as easily as we shared. But again, look at the piece of equipment. So we'd have to get the equipment up there. It'd have to be operated. Are there going to be individuals? Are there going to be remote controlled? There are challenges that we'd be facing. So that's before we even start mining, we also need an ecosystem up there. We need resources so that we need oxygen production and fuels and manufacturing capabilities. We'd have to have transport systems built so we can mine on the moon. That means we'd have to have governance and decision-making. We'd have to have social and political systems in place, economic and technological base, safety standards, and the energy infrastructure has to be there. So we'd have to have fuel production. We live in a world where everything's available to us. So that's why we can do that. But remember, I talked about how difficult it is to go to Africa. The reason it's difficult to go to Africa is not because the materials are not there, is the infrastructure is not there. You need a tremendous amount of energy. You need a road infrastructure. You need the processing plants. And it's very difficult to manage in the governance models that exist in Africa. And so that's not where they're built. So now we also have to take a look at transportation to and from the moon. It's got to be a piece of the puzzle. So there's no rockets and no capacity. If you said today, is there a rocket today that it can get us to the moon? No, we do not have a rocket right now on Earth that can get us to the moon. Now, when we looked at the potential for what we're working on, we've been for Project Moonhot and our 4 phases, the highest probability for us right now is the New Glenn. The Artemis program is a launch every 4 years for 4 astronauts, every 2 years for 4 astronauts at $4.2 billion per launch. Now, this is not a push on the Starship or a slam on the Starship. Numbers have come back. I'm not an expert in orbital mechanics. They've come back that says that the Starship will need 7 to 14 refuelings in order to get to the moon. And one of the challenges when it lands, it could throw up regolith that could sit suspended for a period of time. It's a possibility. The Starship was designed for Mars. Sometimes things are designed for a certain purpose and they require certain types of needs. And then we have the Long March 9 that is also a possibility, but it's still in development. So we don't have anything right now that we can say for sure. So let's take a look then a little bit at the Artemis program. It's still racing to the moon. It's over budget. Right now, it's about $93 billion been spent to date at $4.2 billion per launch every 2 years. That does not include any cargo, the mining supply chain that's necessary. We're looking at an ecosystem that has gone out of control and most likely will not be delivered on the mining side. We're not talking about sending individuals to the moon, on the mining side to hit what we need. But if we're going to go to the mining side, they just announced that they're going to build a nuclear reactor that potentially would go on the moon. For a nuclear reactor to be on the moon, it's the same type of thinking. We have no infrastructure to assemble a nuclear reactor on the moon, no water or cooling, and every nuclear reactor needs that. Massive power just for the mining operations, this won't be enough. No scale reactor that we can even look at. So while there's a lot of sharing of the possibilities on the moon, fantastic. Hopefully for the mining side, you see things a little bit differently. So let's take a look at mining, or get some reality checks here again. If we were to have an operation, we need something like on the left. We'd have to have humans living there. We'd have to have consistent landing cadence. We'd have to have precision mining equipment. We've been shipping to the moon recently, and everything we've sent has failed. That's the picture on the right. The Japanese Slim landed, but upside down. The American failed to reach the moon due to propulsion issues. The Israelis crashed on descent. The Indians, the 2 failed landings. I mean, the Chinese did have a success, but it's limited. And if we're talking about an entire ecosystem where individuals are saying we're off Earth all our mining, oh, come on. I mean, I'd love to believe that's the case, just don't see it. So here's an example. Intuitive Machines sent up a lander. And when they called Greg on our team and they said, we're going to do some mining. So Greg said, well, how far are you going to mine? And they said, 1 foot, 30 cm. Remember, we've gone 293 centimeters, so they're going to go 1 cm. And Greg did some math and he said, you do know if that's hit something hard, it's going to spin like a top. And that's only in the 1 foot. So in addition to that, we have to have constants. For example, right now, today, with the technology we have, in order for us to be able to land and take off, we're going to have hard rock on the moon, rock landing pads. Because if it was in the regolith, it would fly all over. So we'd have to try to control that as much as possible. There's no exceptions. At least today's technology, we'd have to have a hard rock surface and rock landing pads. How are those going to be built? Let's take another jump. We're going to talk about asteroid mining. I hope you're going to have some fun with this one too. We don't make perfect rocks. Mining an asteroid, we'd have to do the same thing that we do on the moon. We'd have to do the same thing on the asteroid. You see, when you take out when you mine and you take the processing, all of that requires chemicals. You don't want to bring back 0.07 grams. You don't want to bring back all the rock, all of it, just to get that number. The math doesn't work. So mining as an asteroid is the same steps that we would be on Earth or on the moon. There's no different. Besides, we added some transport to it that makes it crazy. Now, here is where it goes a little bit sideways. I don't know if you know this, but we can't see 5 meters under Kansas, Berlin, or Tokyo. But we're told that at traveling at 12,000 to 70,000 miles per hour, we're able to see an asteroid, scan it, and tell you what's inside of it. We can't do that on Earth. As a matter of fact, on your left-hand side, we have ground-penetrating radar. This is 2024 radar. It goes 5 meters deep. This is what they see. That's a gas main, a water main, and a utility structure. That's it. So with billions of dollars in tech, we still drill to find oil, water, and materials. We have to. We don't have the tech. Now, if you were to take this picture on the right, let's make it even more complicated. We're traveling at, an asteroid could be up to 70,000 kilometers per hour. It's just flying by. We're flying by at a certain speed also. We're going to be able to see what's inside of it at that same time. I don't know. It's just questionable. And there's a belief that what we see on the top is what's going to be inside. But if you think of it, an asteroid is like a box of chocolates. You think you know what's inside, but when you crack it open, you're always in for surprises. You'll take a bite and you'll see. We can't see. An asteroid surface might be hundreds of meters thick of igneous rock battered by the solar system. We don't know. And some of these layers might be high grade, some may be low grade, but a platinum asteroid, we've never seen one on Earth. We've never seen a full asteroid on Earth of platinum. So the largest platinum we mine is in Montana today. And this is the actual configuration of it. It produces platinum as a byproduct of gold mining at about 10 grams per ton. So we're the largest platinum producers in South Africa at 71,000 ounces per year. These are insignificant numbers. So in the universe, space mining, it just crumbles to all the math. But you probably want to see the math anyway. Again, we've never found an asteroid made of pure composition. They don't exist. We've seen them on Earth. We know what they're like. So we can't see those 5 meters down. And now we're going to travel to this distant rock and try to figure it out. So let's do some math here. Let's try to figure this out using some science behind it or some calculations. Let's assume that we had to get to this asteroid and it cost us $1 trillion to get there and maybe bring it back. what we'd be looking at is a platinum asteroid. And let's assume it was 50% 50% of it was platinum. And this would be the size of 3 football fields. So about 1 million cubic yards, 900 feet by 900 feet by 900 feet. We'd estimate it to be a specific gravity of 12. So that's 12 kilograms per cubic meter. And the weight of the asteroid can be calculated. And we've done that below. So now on Earth, we mine 180 metric tons of platinum annually. That's it. So the price of platinum on Earth in January 25th, 2025 was $932 an ounce. If we were to mine it, was 50%, that would be the equivalent of 13 billion ounces. That's 2,100 years of platinum. Could we use it faster? Sure. And the value of platinum would go to zero once we found something like this. So looking at an asteroid and believing that just because we can see it, we know what's inside of it, that's off. But then to not think of the actual economics behind it, because our world runs on economics, we could run into some severe challenges. But to add another layer about this, the Earth is traveling at 77,000 kilometers per hour through space. It's flying. It's spinning around the sun. There's a moon around it. And we're going to take an asteroid, some people have proposed, and send it back to Earth. We're going to ship it back. Let's say we hauled it back to Earth and threw it. An asteroid the size of a shopping mall got rid of all of the dinosaurs. A shopping mall. Besides, if it hits the Earth, it'll create tsunamis of unbelievable extinction level events and could also knock the moon out of orbit. What can go wrong with that theory? Besides, we're not even going to be able to do that. So what we've just shared with you is something that's going to be difficult for many individuals. What we've said is their life's work is a lie. And I don't think we're going to get a lot of thank yous for this. It's a challenge. With one member of our team for 5 years, I kept on saying, we're not going to mine on the moon. And I was told, I've been doing this for X amount of years. I know better. And I can't tell you how many events I've been to where proposals are answered with, David, I've been doing this for 30 years. I've been doing this for 12 years. My answer is very simple. Just point to where you are on the moon. Just point. Just show me where you are on the moon. Look, innovations come about all the time. Now we have a reality check. Now we have to reassess what we need and what that means for us moving forward. And still, I've had individuals after seeing this deck say, yeah, but we're still going to do it anyway. Okay. But for those of you who are making decisions about our future, for the soon-to-be 10 billion people on this planet, let's hope we use the common sense and go in a different pathway. So let's bring it back down to Earth. What we've been chasing is buried beneath our feet. It already is. You've seen it. The moon and the Earth made of the same material. So if we were to use that construct, that thinking, then we can refocus energy and capital to the right place. But we are right now in a dead zone. We're in the red zone. And what that means is this, is that we're already running out of stability. Our systems are not working. Energy demands are outstripping what we need. There's military situations happening worldwide. We have economic breakdowns. Supply chains are faltering. Ecosystems are collapsing. Geopolitical volatility. Assumptions are no longer valid. We don't have the time for this. We don't have time to waste. And we thought we had time. We did. We thought we had decades to be able to make this happen. And it didn't work out that way. And it's not panic. It's about precision. It's not about going faster. It's about being smarter. It's not about extraction. It's redesign. We have to rethink everything we've thought. So let me introduce to you a concept. Mearth Infinium was where we started with this, of how we can look at things differently. We have narrow vein mining equipment. Narrow vein mining equipment, instead of bringing down that 45-foot wall, we can extract the material, which means less energy taken, less material, less that has to be processed, less moved to the surface, less through that entire value chain. We can change the economics, and it's robotic. So it's not human-oriented, it's machine-oriented. And the machinery has already been put into production. It's already worked. So this is remote controlled, operated, and then autonomous once it's set into a condition and creates a path that works, that will continually do the same function. And these were being managed on the surface while the equipment is underground. So let's take a look at the mining industry to get a sense of where they are. We go back to 1982. And in 1892, you'll see that at that point, we were dropping a little shy of 1,000 ton per person per year. That's what was delivered. And if you go to the year 1928, you'll see that escalation. Technology was introduced into the mining ecosystem, and it came up to where a miner was dropping about 4,000 ton of rock per year. Today, we're at 4,000 ton of rock per year. So a miner is producing a lot more, double the amount that they were just in 1982. And the projection is with some of the new equipment that's out there, and by the way, there is no autonomous robotic equipment anywhere in the world that is working. We've seen, we evaluated, we know what's there. There is nothing. It will bring us up to about 8,000. But that won't meet the needs of those 293 mines. It won't meet the needs of what we need for data centers and mobile phones. It won't meet the needs for aircrafts in our homes to live the life that we've been expecting. We'd have to throttle back. But humans don't stop. I don't think you're looking to cut back on your phone and other devices. Humans tend to move forward. So what do we introduce? Autonomous robotics. Now, we have evidence of this working. This equipment that we're talking about has 75 man years of data where it was producing the equipment, the rock from underground. So it's operationally specific with this data. We also have 400 videos of it in production. So here's an analogy or a story of what happened and in one scenario. There was one mine that these two guys were running in Ontario's division of Inco. And Greg was charged with coming up with a technology that would turn the mine into a factory. And he did. It took him years, took about $300 million, and he figured out what was necessary to make that happen. Then that was put into the technology, and they had two individuals on the surface. And they were running 2 scoop trams each, which is like that picture that you see of the yellow scoop tram up there. And they were moving about 8,000 ton a day combined. There were 450 other individuals running 100 scoop trams, and their total output was 27,000 ton per day. The math is just unbelievably difficult to argue with. So what our equipment can do is it can go from the 8,000 ton per year per person to anywhere between 500,000 to 1 million ton per person per year. It changes the formulaics of all extraction worldwide. And not a single manufacturer has anything close to something that we can deliver. So here's the question. Why have we been talking about mining? We're Project Moon Hut. That's what we're talking about space and all the opportunities there, because Project Moon Hut has never been about mining. It's always been about Earth. See, what happened was, and I'll give you this scenario, I've never been a space person. I still don't look up. Project Moon Hut has grown. We have individuals worldwide who are helping us. You can look at other videos to see in multiple different categories. We have a podcast series called The Age of Infinite. And we've had on some of the most brilliant individuals in the Beyond Earth ecosystem sharing with us their thoughts. There's also another one called Redefining Tomorrow. Because of Project Moon Hut, I was introduced to Hans Koenigsmann, who is the number 4 hire at SpaceX. He's the guy for putting up the Falcon. We had a great 2-hour pre-interview. We had a talk afterwards. So the interview was just a piece of it. I think it was about 3 hours. Most of our interviews go anywhere from 2 to 5.5 hours. And when we were talking, I shared with him something that we're working on internally. And he said, you need to speak to, he did say after watching, he's seen what we've created for the moon and for Earth. And he said, SpaceX is not thinking as big as you are. Those were his exact words. So what ended up happening was he said, you need to speak to an orbital mechanics expert. And we introduced us to C with Mike Lux. We ended up bringing a team of individuals onto the call. Our team from Mearth Space Industries, Project Moonhot, we brought them together, and we had one individual from McKinsey who's been on our team. McKinsey's been on our team, helping us out to figure this out. And when we were done, they said that transport vehicle is not worth its weight and its capability. It won't do it because of the economics, because of the energy that it needs to do the orbital mechanics. It was just down to energy. And when we were done speaking with Mike, he said, you have to talk to this guy, Greg. And Greg and I have this conversation, and we talk about Project Moonhot, what we're working on, and he talks about mining. And he knew at that point that I had already operated. I'm more like a guy who works with toys compared to him. And we had a great call, and he said, you're the first person in 25 years who understood what I was talking about. That was a nice compliment. We ended up talking, and I sent him an NDA, and he didn't sign that NDA for 14 hours of calls, about 6 or 7 calls we spoke. And then he did. And we decided we'd work together to build Mearth Infinium. And so we're about improving how we live on Earth for all species. So we got here because we were thinking differently. If we had not been thinking about the moon, never would have had a podcast series, never would have met Hans, never would have met Mike, never would have met the team at McKinsey, never would have had the call, and never would have met Greg. The combination of all those pieces got us here. So thinking about Beyond Earth has a lot of value. And if you watch the Project Moonhot 2025 video, it's about 1 hour and 40 minutes long, you'll see that there are answers there for our future. So with that said, we are looking for $1 billion, which is not a lot if you learned about mining already, to be able to take 20 mines and produce high-performing mines. The only difference is we don't need 15 to 20 years. Our equipment can go into an existing mine and start to leverage it. We could be operational in a mine that's barely functional today within 2 years, and we can start delivering materials at a very quick pace. We could reshape the entire amount of rare earth materials, because that's the focus, that are available to the world, which would stop us from arguing, fighting. And we can then have the tools that we need for the future. But if you're interested in a little more, we are looking for $2 billion. What does it do? It changes the entire equation. We're still going to take those 20 mines, but we're going to create robotic factories to drop the cost of equipment, because that one piece of equipment you saw, you need about 50 of them, but that one piece of equipment costs about $5 million to build. So by building this into our equation, we then can add more pieces of narrow vein mining equipment into the mines and create higher levels of extraction. We also we're working on the processing and how to be able to break rock, so that it's less costly. So this could feed, as we build this out, the entire world's needs for the next several hundred years by reshaping how we look at mining and where the money goes. So if you're considering Beyond Earth, hopefully you've thought differently. If you're considering the possibilities of what we're delivering, we need a call. We'd love to talk. So with what we've shared so far today, it wasn't a detour to talk about mining. It wasn't a detour to go into this. It was the experience of learning about what we need to be able to do in the process of developing and for the 10 billion people on this planet. So Project Moonhot will have 8 people, 90 people, 578, 1,644 people on the moon over the next 40 years. But the one thing that we do still need on Earth is the ability to extract at a cost variable that gives us the opportunity to thrive. And this is one of those solutions. So with that said, I hope you learned a lot from this sharing. I hope that when you're thinking of the future, when it comes to mining on the moon or an asteroid, you take a second guess. And if you're interested in joining Project Moonhot, we'd love for you to reach out to us. If you're interested in Mearth Infinium, if you're an investor of any sort, we'd be interested in talking. That said, I'm David Goldsmith, and thank you for listening.